The St. Francis Dam was conceived and executed within a specific institutional and technical context that shaped every subsequent decision. Between 1905 and 1913, the city of Los Angeles had constructed the Los Angeles Aqueduct, a 375-kilometer conveyance system designed to transport approximately 12 cubic meters per second of water from the Owens River drainage on the eastern slopes of the Sierra Nevada to the San Fernando Valley. This system was designed, constructed, and administered by the Los Angeles Bureau of Waterworks and Aqueduct under the direction of William Mulholland, who served as chief engineer. Mulholland had begun his career in 1877 as a laborer maintaining water distribution canals and had risen through the organization without formal engineering education, relying instead on direct observation, technical reading, and accumulated operational experience. By 1924, Mulholland was recognized as the principal architect of Los Angeles's water infrastructure and wielded substantial autonomy in project conception, site selection, and design approval. The St. Francis Dam was authorized as a storage facility to provide operational flexibility in the aqueduct system and to serve as a reserve supply during periods of peak demand or reduced inflow. The site selected was located in San Francisco Canyon, a tributary valley to the Santa Clara River, approximately 64 kilometers northwest of downtown Los Angeles and 80 kilometers from the primary Van Norman Reservoir complex in the northern suburbs. The topography consisted of a relatively narrow valley with moderate relief, bounded on the west by slopes composed of Paleogene sedimentary conglomerate, and on the east by slopes of Cretaceous metamorphic schist. A natural spur extending from the western hillside created a constriction in the valley, downstream of which the valley widened into a basin suitable for reservoir storage. The Los Angeles Aqueduct passed through tunnels excavated high in the eastern slopes above the proposed dam site, allowing gravity diversion into the reservoir without additional pumping infrastructure. Construction of the St. Francis Dam commenced in August 1924. The design adopted was a concrete gravity arch structure, a configuration in which the dam relies primarily on its own mass to resist the horizontal thrust of impounded water, with modest curvature in plan to provide limited arch action between abutments. The initial design specified a dam 56 meters in height above the original streambed, with a nearly vertical upstream face and a stepped downstream face that transitioned to a base width of approximately 53 meters. The dam was to be constructed as a monolithic mass concrete structure without provision for contraction joints. This design approach was not developed through formal structural analysis, but was instead copied directly from the Hollywood Dam, later renamed Mulholland Dam, a similar structure completed in 1924 approximately 60 kilometers to the south within the Los Angeles city limits. The Hollywood Dam had been designed with minimal formal calculation, relying instead on empirical proportioning and precedent from earlier gravity dam construction. During construction of the St. Francis Dam, a decision was made to increase the dam height by approximately 6 meters to increase reservoir storage capacity. This modification was implemented by adding a vertical upper wall section to the dam crest without increasing the base width or otherwise altering the downstream geometry. The resulting structure stood 62 meters above the original streambed elevation, with a crest length of approximately 213 meters along the main dam body and an additional wing wall extending 180 meters along the western hillside spur. Photographic evidence from the construction period suggests that the actual extent of the dam's toe may have been less than the design dimension of 53 meters, potentially reducing the structure's stability margin with respect to both rotational overturning and sliding along the foundation contact. The increase in height without corresponding increase in base width reduced the dam's factor of safety against both failure modes when subjected to the horizontal hydrostatic pressure of a full reservoir. The foundation preparation for the St. Francis Dam involved excavation to remove weathered surface materials and expose competent bedrock. This excavation varied in depth from approximately 1 to 4 meters across the dam footprint, depending on local soil thickness and degree of bedrock weathering. A cutoff trench was excavated beneath the upstream face of the dam and backfilled with concrete to provide a nominal barrier to seepage beneath the structure. This cutoff trench was approximately 1 meter wide and 1-meter deep dimensions that were modest compared to contemporary practice for dams of similar height and storage capacity. No grout curtain was installed to seal fractures or bedding planes in the foundation rock beneath the dam. Drainage provisions were limited to a series of relief wells and drains installed beneath the central portion of the dam structure. These drainage features did not extend beneath either the eastern or western abutment sections. No drainage gallery or inspection tunnel was incorporated within the dam cross-section. The absence of foundation drainage beneath the abutments reflected a judgment by Mulholland that such drainage was necessary only where bedrock exhibited conspicuous fracturing or fissuring. In his view, the rock in both abutments appeared sufficiently homogeneous and competent to require no special provisions for pressure relief. This assessment was made without formal geological consultation and without subsurface exploration beyond the shallow excavations required for site clearing. The significance of this omission would become apparent only in retrospect. Modern understanding of uplift pressure in dam foundations recognizes that hydrostatic pressure from an impounded reservoir can be transmitted through interconnected fractures, bedding planes, and cleavage surfaces in foundation rock, creating an upward force that reduces the effective weight of the dam and thereby reduces resistance to sliding and overturning. By 1912, published literature on dam design had documented this phenomenon and had identified foundation drainage as a critical safeguard. The failure of the Austin Dam in Pennsylvania in 1911 had been attributed in part to inadequate control of uplift pressure. These precedents were apparently not incorporated into the design approach adopted for the St. Francis Dam. The geology of the dam site was characterized by the presence of two distinct lithologic units. The western abutment and foundation consisted of the Vasquez conglomerate, a Paleogene sedimentary formation composed of poorly cemented cobbles and boulders in a matrix of clay-rich sand and silt. The eastern abutment and a portion of the central foundation consisted of the Pelona schist, a Cretaceous metamorphic rock characterized by well-developed foliation and pervasive micaceous mineralogy. These two units were juxtaposed along the San Francisquito Fault, a northeast trending structure whose surface trace passed directly through the dam site beneath the western portion of the dam. The fault was marked by a zone of gouge and brecciated rock more than 1 meter wide, flanked by zones of intensely fractured and veined material. The fault had been mapped in regional geological surveys prior to construction of the dam, but these maps were not consulted during site selection or design. The presence of the fault was therefore not incorporated into any assessment of foundation competence or seepage potential. The mechanical properties of the Vasquez conglomerate were fundamentally unsuitable for dam foundation purposes. Laboratory testing conducted after the dam failure determined unconfined compressive strength values ranging from approximately 1.5 megapascals in dry conditions to negligible strength when saturated. The rock's matrix contained clay minerals with high plasticity and swelling potential. When exposed to water, the clay-rich matrix absorbed moisture, leading to volumetric expansion and progressive loss of cohesion. The conglomerate also contained numerous thin seams and veinlets of gypsum, a calcium sulfate mineral that is moderately soluble in water. Prolonged exposure to percolating water would dissolve gypsum, creating enlarged seepage pathways and further reducing the rock's effective strength. In the semi-arid environment of San Francisquito Canyon, the conglomerate in its natural, unsaturated state presented no obvious signs of instability. Only upon saturation beneath a reservoir would its inadequacy become apparent. The Pelona schist exhibited a different set of mechanical characteristics. The rock possessed moderately high intact strength, with unconfined compressive strength values in the range of 80 to 100 megapascals in laboratory testing of small specimens. However, the rock mass strength, the effective strength of the rock when foliation planes and fractures are considered, was far lower. The foliation in the schist consisted of closely spaced parallel planes defined by aligned mica minerals along which the rock could separate with minimal resistance to shear. The orientation of this foliation at the dam site was approximately parallel to the valley slope, dipping into the hillside at angles between 30 and 50 degrees from horizontal. This orientation was mechanically unfavorable for slope stability, as it facilitated sliding of rock masses parallel to the foliation planes under gravitational and hydraulic loading. The schist also contained numerous cross-cutting fractures that subdivided the rock mass into irregular blocks. Collectively, these discontinuities rendered the schist susceptible to progressive deformation and potentially unstable under conditions of increased pore pressure or reduced effective stress. Subsequent geological investigation revealed evidence that the eastern abutment had been the site of prehistoric landsliding. Multiple relic slip surfaces were identified within the hillside schist, defining lenticular slide masses that had moved downslope along planes subparallel to foliation. These landslides were ancient features, stabilized under natural conditions prior to construction of the dam. Their presence, however, indicated that the hillside was inherently susceptible to renewed movement if stabilizing conditions were altered. The placement of a large concrete structure at the base of the slope, combined with saturation of foundation rock and introduction of hydrostatic pressure from an adjacent reservoir, constituted precisely such an alteration. The potential for reactivation of these latent slip surfaces was not evaluated prior to construction, as no detailed geological investigation of the site was conducted. The design philosophy that guided construction of the St. Francis Dam was one of empirical precedent and conservative proportioning rather than rigorous analytical calculation. Mulholland and his design staff did not perform detailed stress analyses of the dam cross-section, load distribution on the foundation, or stability calculations incorporating realistic material properties and loading conditions. The dam's geometry was instead based on visual similarity to the Hollywood Dam, adjusted for the greater height required at the St. Francis site. This approach was not unusual for the period, particularly for relatively small dams constructed under the authority of municipal agencies. However, it presupposed that site conditions at St. Francis would be comparable to those at Hollywood, an assumption that was not verified. The absence of formal design calculations meant that there was no quantitative basis for assessing the adequacy of the dam's proportions, the significance of the height increase implemented during construction, or the sensitivity of stability margins to variations in foundation properties, uplift pressure, or material strength. The institutional context in which the St. Francis Dam was designed and constructed was characterized by minimal external oversight. At the time of construction, California law exempted municipal water agencies from state-level review of dam design and construction. The Division of Water Rights, the state agency responsible for dam safety, had no jurisdiction over projects undertaken by cities or special districts. Consequently, the St. Francis Dam was not subject to independent technical review by engineers or geologists outside the Los Angeles Bureau of Water Works and Aqueduct. There was no requirement for formal design documentation, no mandate for geological investigation, and no mechanism for third-party verification of construction quality or conformance to design intent. Mulholland's authority within the Bureau was effectively absolute. The Board of Commissioners that governed the agency consisted of appointed officials with no technical training, who deferred to Mulholland's judgment on all engineering matters. This concentration of authority in a single individual, operating without formal accountability or technical review, created conditions in which judgments based on incomplete information, untested assumptions, or personal confidence could be implemented without challenge. The operating philosophy for the reservoir once construction was complete was similarly informal. Responsibility for monitoring the dam's condition was assigned to a resident dam keeper, whose duties included visual inspection of the structure and observation of seepage flows. No formal inspection protocol was established, no quantitative criteria were defined for evaluating observed conditions, and no escalation procedure existed for anomalies that might warrant further investigation. The assumption was that any significant distress in the dam or foundation would manifest as visually obvious cracking, deformation, or leakage that would be self-evident to an attentive observer. This assumption rested on the expectation that the dam and foundation would behave in a predictable manner consistent with the designer's conceptual model of the structure. It did not account for the possibility that observed conditions, such as seepage flows, minor cracking, or localized settlement, might be symptomatic of progressive failure mechanisms not anticipated in that conceptual model. Reservoir filling commenced in March 1926, when aqueduct water was first diverted into the reservoir basin, The reservoir level rose gradually as water accumulated, with interruptions corresponding to periods of reduced aqueduct flow or increased downstream demand. During this period, vertical shrinkage cracks developed in the downstream face of the dam. Such cracks are common in mass concrete gravity dams, resulting from thermal contraction as the interior of the concrete mass cools following hydration of cement. These cracks typically extend from the exposed surface into the dam, propagating along planes of least tensile resistance. In an unreinforced monolithic structure like the St. Francis Dam, such cracks would be expected to develop along approximately radial and vertical planes in the Central Valley section, and along inclined radial planes in the abutment sections. The presence of these cracks was noted during routine inspections, but was not regarded as indicative of structural distress. This interpretation was consistent with contemporary understanding of mass concrete behavior and was not unreasonable given the limited information available. By April 1926, the reservoir level had risen to the elevation of the fault trace where it crossed the foundation beneath the dam. Seepage was observed emerging from the western abutment in the vicinity of the fault outcrop. This seepage was attributed to flow through the fault gouge and adjacent fractured rock. The flow rate was estimated as modest and was judged to be within acceptable limits for a structure of this type. No corrective measures were undertaken. Over the following months, various minor leaks were observed at different locations along the dam's downstream face and abutment contacts. These leaks exhibited variations in flow rate corresponding to changes in reservoir level and to seasonal temperature variations affecting concrete expansion and contraction. None of the observed leakage flows were regarded as sufficiently anomalous to warrant detailed investigation or remedial action. The interpretation framework applied to these observations was one in which seepage through and beneath dams was expected, provided that flow rates remained stable and no significant erosion or piping was evident. On March 7, 1928, the reservoir reached spillway elevation for the first time, achieving its maximum design storage capacity of approximately 38,000 acre-feet. In the week preceding this date, inspections had noted an increase in seepage flow from several locations in the western abutment. These flows were turbid, indicating that the percolating water was transporting fine-grained sediment. Turbid seepage is a potential indicator of internal erosion or piping within the foundation or embankment material, a mechanism that can lead to progressive enlargement of seepage channels and eventual structural failure. However, in the context of the St. Francis Dam, a concrete structure founded on rock, rather than an earthfill embankment, turbidity was attributed to surface erosion of weathered rock or soil materials rather than subsurface piping. This interpretation was consistent with the expectation that seepage through rock foundations would follow discrete fractures or bedding planes, rather than developing self-enlarging erosion channels as in soil. On the morning of March 12, 1928, the dam keeper discovered a new leak in the western abutment, discharging muddy water at an estimated rate of approximately 75 liters per second. He immediately notified Mulholland, who arrived at the site later that morning accompanied by Harvey Van Norman, his assistant. They inspected the leak and observed that the flow exhibited periodic surging, a pattern of alternating higher and lower discharge rather than steady flow. Mulholland judged that the turbidity of the water was likely due to surface erosion and that the surging might reflect transient variations in reservoir level or groundwater pressure. He concluded that the situation, while requiring attention, did not constitute an immediate threat to the dam's safety. He indicated that corrective measures would be undertaken, but could be deferred to a convenient future date. This assessment was communicated to the dam keeper, and Mulholland and Van Norman departed the site. The judgment rendered by Mulholland on the morning of March 12 was based on his interpretation of the observed conditions within the framework of his accumulated experience and his conceptual understanding of how the dam and foundation should behave. He had inspected numerous dams and water structures over his career and had developed intuitive criteria for distinguishing normal operational conditions from indicators of distress. The seepage flow observed on March 12, while larger and more turbid than previous flows, did not exceed the bounds of what Mulholland considered plausible for a structure of this type at full reservoir. The surging of the flow, rather than being interpreted as evidence of subsurface erosion or structural movement, was rationalized as a transient hydraulic phenomenon. This interpretation was not implausible given the information available. However, it was predicated on the assumption that the foundation materials were behaving in a stable and predictable manner, an assumption that was, by that time, no longer valid. At approximately 8:30 p.m. on March 12, a family driving on the canyon road that passed above the eastern abutment of the dam encountered a section of roadway that had subsided approximately 30 centimeters, creating a distinct step across the road width. The road at this location was situated approximately 30 meters upstream of the dam crest, on a slope composed of Pelona schist. The subsidence indicated that a portion of the hillside had moved downward and outward toward the reservoir. This movement was consistent with incipient landsliding along foliation plains within the schist, driven by reduced shear resistance due to elevated pore pressures in the rock mass. The family did not immediately report the road damage, and news of the incident did not reach dam operating personnel until after the dam had failed. However, the timing of the observed subsidence, approximately 3 hours before the final collapse, indicates that large-scale deformation of the eastern abutment was already underway by early evening on March 12. The St. Francis Dam failed at 11:57:30 p.m. on March 12, 1928. The precise timing is established by the recorded failure of an electrical transmission line supported on the eastern abutment, which caused a logged interruption at a downstream substation. Within seconds of this initial failure, the dam underwent progressive collapse in which the eastern and western wings of the structure were displaced downstream and destroyed, while a central section of the dam, subsequently termed the tombstone, remained standing. The failure released the entire reservoir volume in a period estimated at 70 minutes, generating a flood wave that propagated downstream through San Francisco Canyon, into the Santa Clara River Valley, and ultimately to the Pacific Ocean. The flood caused extensive destruction of infrastructure and agricultural land and resulted in at least 432 confirmed fatalities, with some estimates suggesting a higher toll. The failure of the St. Francis Dam constituted the deadliest civil engineering disaster in 20th century United States history and precipitated immediate scrutiny of the design, construction, and operational practices that had permitted such a catastrophic failure to occur. The question that must be addressed in any forensic analysis of this failure is not merely what physical processes caused the dam to collapse, but why those processes were not anticipated, why warning signs were not interpreted correctly, and why the design and institutional framework permitted a structure of this type to be constructed and operated at this site. The answers to these questions reside not in any single error or omission, but in the systematic interaction of multiple factors: inadequate site investigation, reliance on empirical rather than analytical design, absence of formal external review, concentration of decision authority, and application of an interpretive framework that could not accommodate observations inconsistent with prior expectations. The following chapters reconstruct the sequence of events leading to failure, examine the physical mechanisms that produced collapse, and identify the latent organizational and technical conditions that made failure, if not certain, at least structurally probable. The failure of the St. Francis Dam was not the result of a single catastrophic event or isolated error, but rather the culmination of multiple latent conditions that existed within the technical system, the organizational structure, and the decision-making environment long before the reservoir was filled. These conditions, individually insufficient to cause failure, interacted in ways that progressively constrained the available solution space and created pathways toward irreversible outcomes. Understanding these latent conditions requires examining not only the physical characteristics of the dam and its foundation, but also the cognitive frameworks, institutional norms, and professional practices that shaped how information was gathered, interpreted, and acted upon. The most fundamental latent condition was the absence of comprehensive geological investigation prior to site selection and design. Standard practice in dam engineering, even in the 1920s, recognized that foundation geology constituted the primary determinant of site suitability, and that surface observations alone were insufficient to characterize subsurface conditions. Exploratory drilling, test pits, and detailed mapping of bedrock lithology, structure, and discontinuities were understood to be essential for evaluating bearing capacity, permeability, and potential failure modes. However, no such investigation was conducted at the St. Francis site. The decision to construct the dam at this location was based on topographic convenience, the presence of a natural valley constriction suitable for a dam, proximity to the aqueduct alignment, and absence of existing development that would require land acquisition or relocation. Geological suitability was assessed only through visual inspection of surface exposures during site clearing operations. This approach reflected a broader pattern in Mulholland's professional practice. His career had been built on pragmatic problem-solving and empirical judgment rather than formal analytical methods. He had successfully designed and constructed the Los Angeles Aqueduct, a project of considerable technical complexity, without formal engineering education and without reliance on outside consultants. This success reinforced a belief that direct observation, accumulated experience, and sound practical judgment were sufficient for making engineering decisions. The institutional culture of the Los Angeles Bureau of Water Works and Aqueduct reflected this philosophy. The organization valued operational effectiveness, decisiveness, and loyalty to leadership. It did not cultivate habits of systematic documentation, formal analysis, or critical review of decisions made by senior personnel. There was no expectation that Mulholland's judgments would be subjected to independent verification, and there was no mechanism within the organization for subordinates to challenge those judgments even if they had reservations. The geological conditions actually present at the St. Francis site were fundamentally inconsistent with the assumptions implicit in the dam's design. The western abutment and a portion of the central foundation were underlain by the Vasquez conglomerate, a sedimentary formation that had been described in prior geological literature as weak, poorly consolidated, and prone to disintegration when saturated. A 1911 report prepared by the Bureau's own staff during route selection for the Los Angeles Aqueduct had explicitly identified the Pelona schist along the eastern wall of San Francisco Canyon as unstable fractured material that should be avoided. This report was filed within the Bureau's records, but was apparently not consulted when the dam site was selected 13 years later. The omission is significant not because the earlier report specifically addressed the dam site, it did not, but because it demonstrates that relevant geological information existed within the organization's institutional memory and was not retrieved or applied when needed. The presence of the San Francisco Fault beneath the dam site was similarly documented in publicly available geological maps but was not incorporated into site evaluation. The fault had been mapped by the United States Geological Survey and was shown on regional geological compilations available prior to 1924. Consultation of these maps during site selection would have revealed the fault's presence and should have prompted further investigation of fault zone characteristics, potential for seismic activity, and implications for foundation, permeability, and stability. However, geological maps were not routinely consulted by civil engineers in municipal water agencies during this period, particularly when those engineers lacked formal training in geology. The conceptual framework within which Mulholland operated did not include geological structure as a primary design consideration. His focus was on topography, hydraulics, and concrete proportioning domains in which he had extensive practical knowledge. Geology was regarded as a secondary concern, relevant primarily to the extent that obviously unsuitable materials such as loose soil or heavily weathered rock could be identified and excavated. The mechanical properties of the Vasquez conglomerate were such that the material could not sustain the compressive stresses imposed by the dam under reservoir loading without undergoing progressive deformation. Laboratory testing conducted after the failure established that the conglomerate's unconfined compressive strength in a saturated state was less than 2 megapascals. By comparison, the bearing stress beneath the upstream heel of the dam, where the full hydrostatic pressure of 93 meters of waterhead acted on the foundation, would have been approximately 1.5 megapascals in the vertical direction alone. When the inclined components of stress, due to the dam's geometry, and the lateral thrust from arch action are included, the total stress magnitude in the foundation approached or exceeded the material's strength capacity. Progressive yielding of the conglomerate beneath the dam would produce differential settlement, with greatest deformation occurring where stresses were highest, specifically in the upper portions of the western abutment, where the dam was tallest and where the conglomerate thickness was greatest. This differential settlement would induce additional stresses in the dam structure itself. A monolithic concrete dam, founded on yielding material experiences internal tensile stresses as different portions of the structure settle by different amounts. These tensile stresses would be concentrated in regions where settlement gradients were steepest, typically at the boundaries between competent and incompetent foundation materials or at geometric discontinuities in the structure. In the case of the St. Francis Dam, such boundaries existed at the contact between conglomerate and schist near the center of the dam and at the transition between the main dam and the western wing wall. The dam's concrete had already developed shrinkage cracks due to thermal contraction during curing. Superposition of additional tensile stresses from differential foundation settlement would tend to propagate these existing cracks and potentially open new fractures. The absence of reinforcement in the concrete meant that once cracks extended through the full thickness of the dam, adjacent blocks of concrete would be separated and could move independently. The phenomenon of foundation uplift pressure constituted another latent condition whose significance was not adequately appreciated in the dam's design. When a reservoir is impounded against a dam, hydrostatic pressure is exerted not only on the upstream face of the structure, but also within the foundation rock beneath and adjacent to the dam. Water from the reservoir infiltrates into fractures, bedding planes, and other discontinuities in the bedrock, creating pore pressures that reduce the effective normal stress acting across potential sliding surfaces. The magnitude of this pore pressure depends on the permeability of the foundation rock, the connectivity of flow paths, and the effectiveness of drainage measures. In the absence of a deep cut-off wall or grout curtain to impede flow, and in the absence of relief wells or drainage galleries to dissipate pressure, the uplift pressure distribution beneath a dam may approach the full hydrostatic head of the reservoir. The mechanical consequence of uplift pressure is a reduction in the effective weight of the dam, which in turn reduces resistance to sliding and overturning. The factor of safety against sliding, defined as the ratio of resisting forces to driving forces, is directly proportional to the effective normal force acting on the foundation contact. If uplift pressure increases, the effective normal force decreases, and the factor of safety decreases correspondingly. For the St. Francis Dam, the absence of foundation drainage beneath the eastern and western abutments meant that uplift pressure in these regions could develop to magnitudes comparable to the reservoir head. Mulholland's statement that he considered drainage unnecessary where bedrock appeared homogeneous indicates that he did not recognize the significance of uplift pressure in fractured or foliated rock masses. This judgment was inconsistent with contemporary engineering literature and with the documented experience of other dam failures attributed to uplift. The eastern abutment presented a distinct set of latent conditions related to the orientation and mechanical properties of the Pelona schist. The schist's foliation dipped into the hillside at angles between 30 and 50 degrees, creating planes of weakness that were approximately parallel to the slope surface. The shear strength available along these foliation planes was controlled by friction and by the limited cohesion provided by intact rock bridges between discontinuities. Under natural conditions, with no external loading, and with groundwater levels relatively deep due to the semi-arid climate, the hillside was stable. However, the construction of the dam and the subsequent impoundment of the reservoir altered these conditions fundamentally. The weight of the concrete structure applied a vertical load to the base of the slope, increasing normal stresses on potential slip surfaces within the schist. Simultaneously, infiltration of reservoir water into the hillside elevated pore pressures along foliation planes, reducing effective normal stress and thereby reducing frictional resistance to sliding. Geological investigation conducted after the dam failure identified multiple relict slip surfaces within the eastern abutment, indicating that prehistoric landslides had occurred in this location. The morphology of these features suggested that they were deep-seated rotational or translational slides that had moved along foliation planes and had subsequently stabilized under natural conditions. The presence of these features was not unique to the St. Francis site. Similar ancient landslides were identified along much of the eastern slope of San Francisquito Canyon during post-failure reconnaissance. However, their presence at the dam site was significant because it indicated that the hillside was inherently susceptible to renewed movement if the factors controlling stability, effective stress, pore pressure, external loading were altered. The placement of a large concrete structure at the toe of the slope, combined with saturation from an adjacent reservoir, constituted precisely such an alteration. The design of the St. Francis Dam did not incorporate any factor of safety margin to account for uncertainty in material properties, loading conditions, or construction quality. The dam's proportions were based on empirical precedent rather than analytical calculation, and no formal stability analysis was performed to verify adequacy under credible loading scenarios. This absence of quantitative analysis meant that there was no documented basis for the dam's safety margins or lack thereof. Contemporary practice in dam engineering recognized that factors of safety should be explicitly calculated and should exceed minimum threshold values to account for uncertainties and potential deviations from design assumptions. Typical minimum factors of safety for gravity dams were 2 against sliding and 1.5% against overturning, based on assumed loading conditions that included full reservoir, uplift pressure, and earthquake forces were applicable. Whether the St. Francis Dam met these criteria could not be determined without analysis, and no such analysis was performed. The increase in dam height implemented during construction further reduced whatever safety margins may have existed in the original design. Raising the crest by 6 meters increased the reservoir storage capacity and the hydrostatic force acting on the dam, but did not increase the dam's base width or otherwise enhance its resistance to sliding or overturning. The effect was to increase the driving forces while leaving the resisting forces unchanged, thereby decreasing the factor of safety. If the original design had been marginally adequate, the modified design would be inadequate. If the original design had included appropriate safety margins, those margins would be partially consumed by the modification. The decision to increase the dam height without corresponding structural adjustments reflects either an implicit assumption that the original design had been highly conservative, an assumption that could not be verified without calculation, or an insufficient appreciation of how changes in geometry affect structural stability. Photographic evidence from the construction period, analyzed after the failure, suggested that the actual extent of the dam's downstream toe may have been less than the design dimension. If the concrete pour did not extend to the intended limits, the effective base width of the dam would be reduced, further compromising stability. This discrepancy, if real, would represent a construction deficiency that should have been identified through survey and quality control procedures. However, the Bureau's construction practices during this period did not emphasize formal documentation or independent inspection. Responsibility for verifying conformance to design rested primarily with the resident construction supervisor, who reported directly to Mulholland. There was no independent quality assurance function within the organization and no external oversight by state or federal agencies. Under these conditions, deviations from design could occur without detection or correction. The dam's monolithic construction without contraction joints or other provisions for accommodating differential movement created a structural system with limited redundancy and no capacity for stress redistribution. In a jointed dam, individual blocks can move slightly relative to one another in response to foundation settlement or thermal expansion, without inducing large tensile stresses in the concrete. Joints also provide known planes of weakness that can accommodate cracking in a controlled manner. In a monolithic dam, all deformations must be absorbed by the concrete itself, and cracks develop along planes of least resistance determined by local stress concentrations, material heterogeneities, and thermal gradients. Once formed, these cracks cannot close completely even if external loads are removed, because rough crack surfaces interlock and because some irreversible deformation occurs in the surrounding concrete. The result is a structure that, while appearing intact from external observation, consists internally of multiple blocks separated by partial or complete fractures. The mechanical behavior of such a structure under load is fundamentally different from that of a true monolith. But this difference is difficult to quantify without detailed knowledge of crack locations, orientations, and degrees of separation. The alarm system and monitoring protocols in place at the St. Francis Dam were minimal. The dam keeper was responsible for daily visual inspection of the structure and for noting any unusual conditions such as new cracks, changes in seepage flow, or structural deformation. However, there were no instruments installed to measure concrete strain, foundation movement, seepage quantity, or uplift pressure. The dam keeper had no technical training in structural engineering or dam safety and had no formal criteria for evaluating whether observed conditions were within acceptable limits. His reporting mechanism consisted of notifying Mulholland or Van Norman if he believed a situation warranted their attention. This approach placed the burden of interpretation on an individual with limited technical knowledge and provided no quantitative data that could be used to track trends or identify gradual deterioration. It was consistent with the prevailing assumption that significant distress in a dam would manifest as obvious, unmistakable symptoms rather than as subtle progressive changes requiring instrumentation to detect. The absence of a deep cutoff wall beneath the dam was a design omission that facilitated seepage through the foundation and allowed reservoir water to reach zones of weak material that might otherwise have remained isolated. A cutoff wall, typically a concrete-filled trench excavated to a depth of 1 to 2 times the dam height and extending along the full length of the dam, serves to intercept and block seepage paths through permeable or fractured foundation rock. It also increases the flow path length for any seepage that does occur, thereby reducing seepage quantities and erosion potential. The cutoff provided at St. Francis was only 1 meter deep and 1 meter wide, dimensions that were adequate only for impeding flow through superficial weathered material. Any seepage following deeper fracture systems, bedding planes, or fault zone gouge would bypass this shallow cutoff entirely. The absence of a grout curtain compounded this deficiency. Grouting, the injection of cement slurry or chemical grout into drilled holes to seal fractures and reduce permeability, was established practice for dam foundations by the 1920s and was recognized as particularly important for rock foundations with significant fracturing or jointing. The decision not to grout at St. Francis cannot be attributed to lack of available technology. It reflects instead a judgment that such measures were unnecessary for this site. The organizational culture within the Los Angeles Bureau of Waterworks and Aqueduct was characterized by strong hierarchical authority, loyalty to leadership, and limited tolerance for dissenting views. Mulholland's personality and leadership style reinforced this culture. He was known for decisiveness, confidence, and impatience with prolonged deliberation or second-guessing. Subordinates who raised concerns or questioned his decisions risked professional marginalization. This dynamic created an environment in which information flowed upward through the organization, but critical feedback did not flow downward. Junior engineers or field personnel who observed anomalous conditions or had reservations about design decisions had limited avenues for expressing those concerns in a manner that would influence decision-making. The result was an organizational structure that amplified the judgments of senior leadership while attenuating the perspectives of those with direct operational knowledge. A particularly significant latent condition was the absence of external review or oversight. California's Dam Safety Regulatory Framework in 1928 exempted municipal agencies from state-level review, on the premise that such agencies were publicly accountable and would maintain adequate internal standards. This exemption removed a critical safeguard that might have identified deficiencies in design, construction, or operation. The State Division of Water Rights had statutory authority to regulate privately owned dams, but had no jurisdiction over the St. Francis Dam. Consequently, no independent engineer reviewed the design, no geologist assessed the site, and no inspector verified construction quality on behalf of any entity other than the Los Angeles Bureau itself. This regulatory gap was not unique to California. Similar exemptions existed in other states and reflected a broader assumption that governmental agencies could be trusted to self-regulate. The St. Francis failure demonstrated the fallacy of this assumption and prompted immediate legislative changes to eliminate such exemptions. The training and professional development of dam operators and inspection personnel during this period did not emphasize recognition of incipient failure modes or interpretation of warning signs. The dam keeper at St. Francis had operational responsibilities but no formal education in civil engineering, structural mechanics, or dam safety. His understanding of what constituted normal versus abnormal behavior was based on informal guidance from supervisors and on his own observations over time. This knowledge was largely qualitative and comparative. A condition was judged normal if it resembled conditions previously observed, and abnormal if it represented a significant departure. However, this approach provided no framework for recognizing progressive deterioration or for distinguishing between benign variations and indicators of impending failure. The dam keeper's observation of muddy seepage and surging flow on the morning of March 12 was reported to Mulholland, but neither the dam keeper nor Mulholland interpreted these signs as indicators of imminent structural collapse. The interpretive framework available to them did not include a mental model of how subsurface erosion in weak conglomerate or progressive landslide movement in foliated schist might manifest at the surface. The concept of progressive failure, wherein a structure or foundation gradually loses strength or stability through a sequence of incremental damage events, was not well developed in dam engineering practice of the 1920s. Failures were generally conceptualized as resulting from overload, a flood exceeding spillway capacity, an earthquake exceeding design seismic resistance, or a sudden foundation collapse due to previously undetected voids. The possibility that a dam could fail under normal operating conditions due to gradual deterioration of foundation material or cumulative loss of structural integrity was less widely recognized. This conceptual gap meant that warning signs of progressive failure, such as increasing seepage, turbidity, or localized deformation, might be rationalized as transient anomalies rather than interpreted as evidence of an ongoing failure process. The physical configuration of the dam site itself contributed to the latent failure conditions. The narrowness of the valley and the presence of the natural spur on the western side created a geometrically constrained site in which the dam had to accommodate significant variations in foundation elevation and material properties over a relatively short horizontal distance. The central portion of the dam rested on schist at relatively low elevation, while the western wing extended up the conglomerate slope to maintain a continuous crest. This configuration meant that different sections of the dam were subjected to very different stress conditions and were supported by very different foundation materials. The potential for differential movement and for stress concentrations at material boundaries was inherently high. A more favorable site would have provided a uniform foundation material across the full dam length and a symmetric valley geometry that would distribute loads more evenly. The decision to construct a concrete gravity dam rather than an alternative design such as an earth or rockfill embankment reflected a preference for concrete construction that was widespread in the early 20th century. Concrete dams were perceived as more permanent, more controllable during construction, and less susceptible to erosion or piping than earthfill dams. However, concrete dams impose much higher bearing stresses on foundation materials than embankment dams of equivalent height, and they are less tolerant of foundation deformation. An earthfill dam can accommodate moderate differential settlement through internal adjustment of the fill material, whereas a concrete dam subjected to differential settlement develops cracks and internal stress concentrations. For a site with weak or variable foundation conditions, an embankment design might have been more appropriate. The choice of a concrete gravity design presupposed that the foundation was competent and uniform, an assumption that was not verified at St. Francis. The schedule pressures and resource constraints under which the dam was designed and constructed also constituted latent conditions. The Los Angeles water system was under continuous demand for expansion to serve the city's rapidly growing population. New storage capacity was needed urgently, and delays in project delivery were viewed as impediments to the city's economic development. This urgency created an organizational bias toward rapid decision-making and abbreviated planning processes. Comprehensive site investigation, detailed design analysis, and extended construction schedules were seen as costly and time-consuming. The institutional incentive structure rewarded timely project completion and cost control rather than thoroughness of design or conservatism of safety margins. Under these conditions, decisions tended to favor expedience over exhaustive analysis, and judgments were made with less information than would be ideal, but with sufficient information to appear reasonable at the time. The cumulative effect of these latent conditions was to create a socio-technical system in which failure was not inevitable in the deterministic sense, but was highly probable given the combination of weak foundation materials, inadequate design provisions, absence of external review, concentration of decision authority, and limited capacity for detecting and interpreting warning signs. No single condition was sufficient to cause failure. The conglomerate alone, or the schist alone, or the fault alone, or the inadequate drainage alone, might have been manageable if other aspects of the design and oversight system had been robust. However, when multiple latent conditions align, when weak materials coincide with inadequate analysis, when organizational culture discourages critical review, when regulatory oversight is absent, and when warning signs are misinterpreted, the probability of catastrophic failure increases dramatically. The St. Francis Dam was a system configured for failure, awaiting only the final triggering conditions that would convert latent vulnerability into manifest collapse. The transformation of latent vulnerability into active failure began not with a single catastrophic rupture, but through a sequence of progressive deterioration events that unfolded over days and hours preceding the final collapse. Understanding this progression requires reconstructing the state of the dam and foundation as the reservoir approached and reached its maximum designed capacity, identifying the physical processes that were initiated by full impoundment, and examining how these processes were interpreted or misinterpreted by those responsible for monitoring the structure. The critical analytical challenge is to distinguish between what was observable at the time and what could be inferred from those observations given the conceptual frameworks and technical knowledge available to the observers. By March 7, 1928, the reservoir level had risen to spillway elevation for the first time since filling operations began in 1926. The reservoir now contained approximately 38,000 acre-feet of water, equivalent to a volume of roughly 47 million cubic meters. The water surface elevation was approximately 564 meters above mean sea level, corresponding to a maximum depth of 93 meters at the dam. This represented the full design capacity of the reservoir and the maximum hydrostatic loading condition for which the dam had been proportioned. The horizontal force exerted by the impounded water on the upstream face of the dam was approximately 380 meganewtons, distributed over the height of the structure according to the triangular hydrostatic pressure distribution. This force was resisted by the dam's self-weight, by shear resistance along the foundation contact, and by any arch thrust that could be developed through bearing against the abutments. The attainment of full reservoir capacity marked a transition in the hydraulic and mechanical state of the foundation. Prior to this point, water infiltration into foundation rock had been limited to elevations below the instantaneous reservoir level, with the upper portions of the abutments remaining unsaturated. With the reservoir at spillway level, water was now in direct contact with foundation rock across the full height of the dam, and hydrostatic pressure was being transmitted into fractures, bedding planes, and foliation surfaces throughout the foundation volume. The rate at which pore pressures within the foundation equilibrated with reservoir pressure depended on the permeability of the rock mass and on the connectivity of flow paths. For highly fractured or foliated rock with interconnected discontinuities, equilibration could occur within hours to days. For less permeable rock with isolated fractures, equilibration might require weeks to months. The Polona schist forming the eastern abutment and portion of the central foundation possessed moderate permeability along foliation planes and cross-cutting fractures, but low permeability across intact rock matrix. The foliation orientation dipping into the hillside at 30 to 50 degrees provided preferential flow paths that were approximately parallel to the slope surface. Water entering these foliation planes from the reservoir would migrate along the planes into the hillside, creating elevated pore pressures at depth. The magnitude of pore pressure at any given point would depend on the hydraulic gradient between that point and the reservoir, and on the resistance to flow along the intervening path. In regions where foliation planes were continuous and open, pore pressures could approach the full hydrostatic head corresponding to the elevation difference between the reservoir surface and the point of interest. In regions where flow paths were constricted or discontinuous, pore pressures would be lower. The mechanical consequence of elevated pore pressure within the schist was a reduction in effective normal stress acting across foliation planes and other potential sliding surfaces. Effective stress, defined as total stress minus pore pressure, controls the frictional resistance available to resist shearing. As pore pressure increases, effective stress decreases, and shear strength decreases proportionally. For a hillside that was marginally stable under natural conditions, the introduction of elevated pore pressures due to reservoir filling could reduce the factor of safety below unity, initiating slope movement. This movement would not necessarily be instantaneous or catastrophic. It could occur as slow creep or as episodic incremental displacements, particularly if the sliding mass encountered irregularities or intact rock bridges along the slip surface that temporarily arrested motion. Evidence of such movement was documented on the evening of March 12 when the Sylve family encountered the broken roadway on the eastern abutment. The road's subsidence of approximately 30 centimeters indicated downward and outward displacement of a block of hillside schist. The location of this displacement, approximately 30 meters upstream of the dam crest, suggests that the sliding mass extended from near the reservoir shoreline down to the base of the dam or below. The timing of the observed displacement, approximately 3 hours before the final collapse, indicates that large-scale deformation of the eastern abutment was actively underway by early evening on March 12. However, because this observation was not reported to dam operating personnel until after the failure had occurred, it did not influence real-time decision-making. The Vasquez conglomerate forming the western abutment and foundation exhibited very different behavior under reservoir loading. The conglomerate's clay-rich matrix absorbed water readily, leading to swelling and progressive loss of strength. Gypsum veins within the conglomerate dissolved upon prolonged contact with percolating water, creating enlarged seepage paths and reducing the material's cohesion. The combined effects of saturation, swelling, and dissolution resulted in a gradual reduction in bearing capacity and an increase in deformability. Under the compressive stresses imposed by the dam, the saturated conglomerate underwent creep-time-dependent deformation at constant stress and localized compression where stress concentrations were highest. Seepage through the conglomerate had been observed from early in the reservoir filling process. Initial seepage flows were clear, indicating that water was moving through existing voids or fractures without mobilizing fine particles. As saturation progressed and the conglomerate matrix began to soften, seepage flows became turbid, indicating that fine-grained material was being transported in suspension. Turbidity in seepage is a recognized warning sign in dam safety because it indicates internal erosion, the progressive removal of material from within the structure or foundation. If internal erosion continues unchecked, it can create enlarged flow channels that further accelerate erosion, eventually producing cavities or pipes that undermine structural support. However, the significance of turbidity depends on the context. In an earthfill embankment dam, turbid seepage is an immediate concern because it indicates active piping in the dam body or foundation. In a concrete dam founded on rock, turbidity was more commonly attributed to surface erosion of weathered rock or mobilization of sediment from pockets of loose material exposed during excavation. During the week preceding March 12, multiple seepage flows were observed in the western abutment, several of which exhibited turbidity. These flows were reported to Mulholland and Van Norman, who inspected the dam on several occasions. Their interpretation was that the turbid water was likely draining from superficial materials or from seams of weathered conglomerate exposed on the downstream slope. This interpretation was consistent with the expectation that the conglomerate, while weak, was not undergoing catastrophic internal erosion. It was also consistent with the broader assumption that the foundation, having been exposed during site clearing and visually inspected prior to concrete placement, was adequate to support the dam under design loading. The possibility that subsurface erosion was actively enlarging flow paths within the conglomerate, and that this process was progressively weakening the foundation, was not considered as a likely mechanism. On the morning of March 12, the dam keeper discovered a new leak emerging from the western abutment. This leak was larger than previously observed seepage flows and was discharging visibly muddy water. The estimated flow rate of 75 liters per second, if accurate, represented a significant volume of seepage and implied the existence of a well-developed subsurface flow path with relatively high permeability. More concerning was the periodic surging of the flow, alternating periods of higher and lower discharge rather than steady flow. Surging in seepage flows can result from several mechanisms. It can occur if the flow path is partially obstructed by mobile sediment that temporarily blocks the outlet, then is flushed out by increasing back pressure, allowing a burst of higher flow until the obstruction reforms. It can also occur if the seepage path includes an underground void or cavity that fills and drains cyclically. In either case, surging indicates that the seepage path is undergoing dynamic changes, that material is moving, cavities are enlarging, or obstructions are forming and clearing. Mulholland and Van Norman arrived at the dam site late in the morning of March 12 to inspect the new leak. They observed the muddy water and the surging flow pattern. Mulholland's recorded statement was that the muddy appearance was likely due to surface erosion and that corrective measures, while necessary, could be deferred to a future date. This judgment has been the subject of extensive analysis and criticism in subsequent years. It has been characterized, by some, as a catastrophic error in judgment, reflecting overconfidence or recklessness. Others have argued that it represented a reasonable interpretation given the information available and the conceptual framework within which Mulholland was operating. To evaluate this judgment fairly requires reconstructing what was known, what could have been inferred, and what alternative interpretations were plausible at the time. The information available to Mulholland on the morning of March 12 consisted of the following observations. The reservoir was at full capacity and had been at or near this level for several days. Seepage flows from the western abutment had been increasing over the past week. The new leak was discharging muddy water at an estimated rate higher than previous flows. The flow exhibited periodic surging, and no other obvious signs of distress, such as large cracks, visible deformation, or structural movement, were evident. The dam keeper reported no unusual sounds, vibrations, or other anomalies. The dam appeared structurally intact, and reservoir level was stable with no indication of accelerating outflow that would suggest a major breach or internal failure. Mulholland's interpretive framework was shaped by his accumulated experience with dams, aqueducts, and water structures over more than 40 years. He had observed seepage in numerous contexts and had developed intuitive criteria for distinguishing benign from hazardous conditions. His expectation was that serious structural distress would manifest as obvious, unambiguous symptoms, major cracking, large-scale deformation, or rapidly increasing seepage indicating loss of reservoir containment. The conditions observed on March 12, while noteworthy, did not exceed the range of what he considered plausible for a dam at full reservoir. The turbidity was attributed to surface erosion rather than subsurface piping, because the dam was founded on rock rather than erodible soil. The surging was rationalized as a transient hydraulic phenomenon rather than evidence of cavity formation or material mobilization. This interpretation was not unreasonable given the information available. However, it was predicated on an assumption that the conglomerate was behaving as a stable, if weak, foundation material, an assumption that was no longer valid by March 12. Unknown to Mulholland, subsurface erosion within the conglomerate had been active for days or weeks, progressively enlarging seepage paths and undermining portions of the foundation. The surging flow was not a transient hydraulic anomaly but a direct manifestation of this erosion process. The muddy water was not surface runoff but sediment mobilized from within the foundation. The failure to recognize these indicators for what they represented was not a function of negligence or incompetence, but rather a consequence of operating within a conceptual model that did not include subsurface erosion in rock foundations as a credible failure mode. The absence of quantitative monitoring data further constrained the available basis for judgment. Had instruments been installed to measure seepage flow rates continuously, the data would have shown not only the absolute magnitude of flows, but also trends over time. An accelerating increase in seepage, particularly if correlated with rising reservoir level, would have provided objective evidence of progressive foundation deterioration. Similarly, if uplift pressure had been monitored through piezometers installed in the foundation, elevated or rising pore pressures would have signaled that reservoir water was penetrating deeply into the foundation and that effective stresses were decreasing. However, No such instruments were installed at St. Francis, and the only data available were qualitative visual observations made during periodic inspections. The decision not to take immediate action in response to the March 12 observations, specifically, the decision not to lower the reservoir level as a precautionary measure, reflected a judgment that the risk of imminent failure was low. Lowering the reservoir would have required releasing water through the outlet works, reducing storage available for downstream delivery, and potentially creating operational difficulties if the reservoir could not be refilled promptly. These considerations were weighed against the perceived urgency of the observed conditions. In Mulholland's assessment, the conditions warranted monitoring and future remedial work, but did not justify immediate emergency drawdown. This judgment was communicated to the dam keeper, who was instructed to continue normal operations and to report any further changes. Between noon on March 12 and the time of final collapse at approximately midnight, the physical processes that had been underway in the foundation continued and accelerated. Subsurface erosion within the conglomerate continued to enlarge flow paths and to remove support from beneath the western portion of the dam. Pore pressures within the schist of the eastern abutment continued to reduce effective stresses along foliation planes, bringing the hillside closer to or beyond the threshold of stability. The weight of the dam and the hydrostatic pressure of the reservoir continued to impose stresses on foundation materials that were progressively losing strength. At some point during this period, the balance of forces transitioned from a marginally stable configuration to an actively unstable configuration in which failure became inevitable. The precise sequence of events during the hours immediately preceding collapse cannot be reconstructed with certainty because no witnesses observed the dam continuously during this period, and no instrumentation recorded the progression of failure. However, physical evidence examined after the failure, combined with analysis of failure mechanics, allows reconstruction of the probable sequence. The eastern abutment, already experiencing progressive landslide movement as evidenced by the road subsidence observed at 8:30 p.m., continued to deform under the combined effects of reduced shear resistance along foliation planes and increased loading from the reservoir. This deformation may have been accelerating as the slope approached or exceeded the critical state for kinematic instability. Simultaneously, the western abutment was experiencing progressive yielding of the saturated conglomerate foundation, where the dam was tallest and the conglomerate thickness was greatest. Bearing stresses exceeded the material's saturated compressive strength, producing incremental settlement. This settlement was not uniform, but was concentrated in zones where the conglomerate was weakest, or where stress concentrations were highest. Differential settlement between adjacent portions of the dam would have induced tensile stresses in the concrete, potentially propagating existing shrinkage cracks or opening new fractures. As the integrity of the dam structure was progressively compromised by cracking, its ability to distribute loads and to resist deformation decreased. The interaction between these two deteriorating conditions, progressive landslide movement on the east and progressive foundation yielding on the west, created a mechanically coupled system in which deformation in one location altered stress distributions in adjacent regions. As the eastern abutment moved outward and downward, support was removed from the eastern portion of the dam. The dam structure, no longer fully restrained on the eastern side, experienced increased cantilever deflection and increased arch thrust toward the western abutment. This increased thrust, transmitted through the already cracked concrete, imposed additional loading on the western foundation, accelerating yielding and settlement. The result was a positive feedback loop. Deformation begat additional stress redistribution, which begat additional deformation, at approximately 11:57:30 p.m. On March 12, this deterioration process reached a critical threshold, the precise trigger for final collapse, whether it was catastrophic failure of the eastern abutment landslide, sudden rupture of the dam structure along a major crack, or a combination of mechanisms cannot be determined definitively. However, the evidence indicates that failure initiated in the eastern abutment. The electrical transmission line supported on the eastern hillside above the dam failed at 11:57:30 p.m., as recorded by instrumentation at a downstream substation. This timing corresponds to the moment of initial major structural displacement. The failure of the transmission line indicates that the hillside was undergoing large-scale rapid movement, either as acceleration of the existing slow landslide or as sudden catastrophic collapse of the slope. The removal of support from the eastern end of the dam by the landslide would have immediately destabilized the eastern wing of the dam structure. The concrete blocks forming this section, no longer restrained by the adjacent hillside and subjected to full hydrostatic pressure from the reservoir, would have been thrust outward and downstream. The loss of the eastern wing would have created a breach in the dam, allowing reservoir water to begin flowing out at high velocity. This outflow would have rapidly eroded the landslide debris and exposed foundation material at the base of the breach. However, the outflow at this stage would have been limited to the width of the breach and would have been constricted by the remaining central and western portions of the dam. The central portion of the dam, the section that ultimately survived as the tombstone, was founded on schist at a lower elevation than the abutment sections and was provided with foundation drainage in the form of relief wells. This drainage, while limited, was apparently sufficient to control uplift pressures beneath this section to a degree adequate to maintain stability. However, the sudden removal of lateral support from the eastern side, combined with the dynamic loading from the initial outflow, subjected the tombstone section to forces for which it had not been designed. Survey measurements conducted after the failure determined that the top of the tombstone had moved approximately 15 centimeters in a radial direction and a similar distance in an easterly tangential direction. These displacements indicate that the tombstone experienced both rotation and lateral translation during the failure sequence, but retained sufficient structural integrity and foundation support to avoid complete collapse. The western portion of the dam, founded on saturated and weakened conglomerate, was subjected to altered stress conditions as the eastern wing failed and the central section moved. The removal of confining stress from the eastern side combined with the increased hydrodynamic forces from the accelerating outflow exceeded the remaining capacity of the western section to resist downstream displacement. Approximately 20 minutes after the initial failure of the eastern wing, based on analysis of flood wave timing and reservoir drainage rates, the western wing of the dam collapsed. This secondary collapse was likely triggered by a combination of mechanisms: increased downstream thrust from the partial breach flow, loss of confining stress from the now displaced central section, and final loss of bearing support as the saturated conglomerate yielded under increased loading. The collapse of the western wing created a second major breach, allowing reservoir water to discharge through both the eastern and western openings simultaneously. The combined outflow capacity through these breaches was enormous, estimated at peak rates exceeding 500,000 cubic feet per second, equivalent to approximately 14,000 cubic meters per second. This flow rate is comparable to the peak discharge of the Mississippi River during major floods and far exceeds the outflow capacity of the dam's outlet works or spillway. The reservoir level dropped rapidly as this outflow continued, falling at rates exceeding 1 meter per minute during the peak discharge period. Within approximately 70 minutes of the initial failure, the reservoir had drained almost completely, leaving only residual pools in low-lying areas of the former reservoir basin. The flood wave generated by this sudden release of water propagated downstream through San Francisco Canyon at velocities estimated at 25 to 30 kilometers per hour. The wave height in the narrow upper canyon reached approximately 40 meters, measured from pre-flood ground surface to the peak water surface elevation indicated by scour marks and debris deposition on canyon walls. As the wave advanced downstream and the valley widened, wave height decreased and wave width increased, with a total volume of water spreading laterally across the available floodplain. Witnesses in the town of Castaic, located approximately 8 kilometers downstream of the dam, reported hearing a rumbling sound beginning at approximately 12:45 a.m. on March 13th, followed shortly by the arrival of the flood wave, which destroyed most structures in the town. Telephone warnings were successfully transmitted to communities further downstream, including Fillmore and Santa Paula, allowing many residents to evacuate to high ground before the flood wave arrived. In Fillmore, the wave arrived at approximately 3 a.m., and in Santa Paula at approximately 3:20 a.m. By this time, the wave had attenuated considerably due to spreading and energy dissipation, but it was still sufficient to cause extensive destruction of structures and infrastructure in the low-lying areas adjacent to the Santa Clara River. The floodwave reached the Pacific Ocean at approximately 5:30 a.m., some 5 hours after the initial dam failure, by which time it had spread across several kilometers of width and had diminished to a depth of a few meters. The human toll of the St. Francis Dam failure was catastrophic. The coroner's official count identified 432 confirmed fatalities, but this number was recognized as incomplete because some bodies were never recovered, having been swept out to sea or buried under debris. Demographic analysis and missing person reports suggested that the actual death toll may have exceeded 450. The majority of fatalities occurred in the upper reaches of San Francisco Canyon and in isolated ranches and work camps in the Santa Clara Valley, where residents received no warning and had no opportunity to escape. In the towns of Fillmore and Santa Paula, where telephone warnings allowed partial evacuation, casualties were substantially lower but still significant, particularly among those who did not hear the warnings or who were unable to reach high ground in time. The material damage extended over more than 87 kilometers of valley length from the dam site to the ocean. Approximately 1,200 structures were destroyed, including houses, barns, agricultural buildings, and industrial facilities. Thousands of hectares of agricultural land were scoured or buried under debris. Multiple bridges, sections of highway and railroad infrastructure were destroyed. The economic cost, estimated at the time as approximately $15 million in 1928 currency, corresponded to several $100 million in present value. However, the economic impact extended beyond direct property damage to include lost agricultural production, costs of emergency response and recovery, and long-term disruption to regional development. The divergence between what observers believed was happening on the morning of March 12 and what was actually occurring beneath the dam represents the central analytical problem of this failure. Mulholland and Van Norman, when they inspected the new leak, believed they were observing a manageable seepage condition that warranted future remedial work but did not constitute an imminent threat. They believed the dam structure was intact and stable. They believed the foundation, while exhibiting some localized weakness, retained adequate bearing capacity and shear resistance. These beliefs were not irrational or unjustified given the visible evidence and the interpretive framework available. However, each of these beliefs was inconsistent with the actual physical state of the system. The dam structure was not intact but was divided into multiple blocks by extensive cracking. The foundation was not stable but was undergoing active progressive deterioration through subsurface erosion and landslide movement. The seepage was not a manageable condition but was symptomatic of advanced internal erosion that would reach a critical state within hours. This divergence between perceived state and actual state is characteristic of many major engineering failures. Systems can appear stable while being on the verge of collapse, because the most critical deterioration processes are occurring in locations that are not directly observable. Instruments, if present, can provide data that reveal these hidden processes, but only if the instruments are monitoring the correct parameters and if the data are interpreted correctly. In the absence of instrumentation, observers must rely on indirect indicator surface manifestations of subsurface processes and must infer subsurface conditions from limited evidence. This inference process is heavily dependent on the observer's conceptual model of how the system should behave. If the model does not include the actual failure mechanism as a credible possibility, the inference will be incorrect even if the observations themselves are accurate. The question that emerges from this analysis is not why Mulholland failed to recognize that the dam was on the verge of collapse. The indicators were ambiguous and the failure mechanisms were not part of his conceptual model, but rather why the system was designed and operated in a manner that made such ambiguity inevitable. A dam equipped with comprehensive instrumentation for monitoring seepage, uplift pressure, foundation displacement, and structural deformation would have provided objective data that could have revealed the progressive deterioration underway. A design process that included thorough geological investigation and rigorous stability analysis would have identified the unsuitability of the site or would have resulted in design modifications to address the identified hazards. An organizational culture that encouraged questioning of assumptions and solicitation of external expertise would have created opportunities for alternative interpretations to be considered. An institutional framework that required independent review would have provided a mechanism for identifying deficiencies before construction proceeded. Each of these safeguards was absent at St. Francis, and their collective absence made the failure probable. The collapse of the St. Francis Dam was not a singular catastrophic event, but rather the terminal phase of a multi-mechanism failure chain in which distinct physical processes interacted, reinforced one another, and ultimately converged to produce total structural failure. Reconstructing this failure chain requires integrating evidence from post-failure site inspections, analysis of the final positions and conditions of dam fragments, examination of foundation surfaces exposed after the flood, laboratory testing of foundation materials, and application of mechanical principles governing dam stability, rock mass behavior, and progressive failure. The objective is to establish a causally complete sequence, to identify each critical link in the chain, to explain how one condition enabled or accelerated the next, and to define the point beyond which recovery was no longer possible. The failure chain began not on March 12, but weeks earlier, when the reservoir first approached full capacity and water began to saturate foundation materials that had remained unsaturated throughout most of the filling period. The Vasquez conglomerate forming the western abutment and foundation was exposed to sustained wetting for the first time, as the reservoir level rose to spillway elevation. The conglomerate's response to saturation was governed by its mineralogical composition and microstructure. The matrix consisted predominantly of clay minerals, primarily montmorillonite and illite, with minor proportions of quartz, feldspar, and calcite. Clay minerals in the montmorillonite group possess sheet-like crystal structures with weakly bonded interlayer spaces that can accommodate water molecules. When dry, these clays are relatively strong and cohesive. When wetted, water molecules penetrate between the structural layers, causing the crystal lattice to expand and reducing interparticle bonding forces. Laboratory testing conducted after the failure characterized the swelling potential and strength degradation of the conglomerate upon saturation. Specimens of intact conglomerate were subjected to immersion in water while confined under stress conditions representative of field loading. The results demonstrated volumetric expansion on the order of 3 to 5% and a reduction in unconfined compressive strength from approximately 2.5 megapascals in the dry state to less than 1.5 megapascals when fully saturated. Triaxial testing under confining pressures representative of in-situ conditions showed that the saturated material exhibited significant time-dependent deformation creep under sustained loading, with strain rates that increased nonlinearly with applied stress. These laboratory findings confirm that the conglomerate, once saturated, could not sustain the bearing stresses imposed by the dam without undergoing progressive deformation. The field-scale consequence of this material behavior was differential settlement beneath the western portion of the dam. Settlement was greatest where the conglomerate thickness was greatest and where the dam height, and therefore the applied bearing stress, was highest. This condition was satisfied in the upper western abutment, where the dam rose to its full height of 62 meters and where the conglomerate foundation extended to depths of 10 meters or more below the dam base. Settlement in this region has been estimated, based on post-failure topographic reconstruction and analysis of crack patterns in the surviving western wing wall, at 10 to 20 centimeters. This magnitude of settlement, while substantial, would not by itself have caused catastrophic failure. However, the gradient of settlement, the rate of change of settlement over horizontal distance, created differential movements that the monolithic concrete structure could not accommodate without cracking. Concrete is a brittle material with high compressive strength but low tensile strength, typically on the order of 1/10 of its compressive capacity. When a concrete structure is subjected to differential settlement, the resulting curvature induces tensile stresses on the convex side of the deformed shape. If these tensile stresses exceed the material's tensile strength, cracks develop and propagate. For the St. Francis Dam, the differential settlement beneath the western abutment would have induced tensile stresses in the upstream face of the dam in this region, promoting crack propagation from the water face into the interior of the structure. These cracks, once formed, provided pathways for reservoir water to penetrate into the dam. Water pressure within cracks exerts a wedging force that tends to open the cracks further, a phenomenon known as hydraulic fracturing. The progression is self-reinforcing. Settlement causes cracking. Cracking allows water penetration, water pressure widens cracks, and widened cracks facilitate additional settlement by reducing the effective area resisting load. Simultaneously, with the mechanical degradation of the conglomerate, chemical dissolution of gypsum veins was occurring within the foundation. Gypsum calcium sulfate dihydrate has a solubility in water of approximately 2.5 grams per liter at typical groundwater temperatures. This solubility is low compared to highly soluble salts such as halite, but it is sufficient to produce measurable dissolution over timescales of days to weeks when flowing water is in continuous contact with gypsum surfaces. The gypsum veins in the Vasquez conglomerate ranged in thickness from a few millimeters to 2 centimeters and were distributed throughout the formation. As seepage water migrated through the conglomerate, it dissolved gypsum from vein walls, widening the veins and creating interconnected cavities along former vein networks. The rate of dissolution depends on the flow rate of water through the vein network and on the degree to which the water becomes saturated with dissolved gypsum. In the early stages of seepage, when flow rates are low and flow paths are long, water may become saturated before it exits the foundation, limiting further dissolution. As flow paths become enlarged and flow rates increase, the water may exit before reaching saturation, allowing continued dissolution at the upstream end of the flow path. This creates a positive feedback mechanism. Dissolution enlarges flow paths. Enlarged flow paths increase flow rates. Increased flow rates enhance dissolution. The eventual result is the formation of pipes or conduits within the foundation, along which substantial volumes of water can flow with minimal resistance. Evidence of piping within the conglomerate was documented during post-failure inspections of the western abutment area, where the dam had stood. Approximately 6 meters of conglomerate had been eroded away during the passage of floodwaters, exposing the subsurface structure of the formation. Investigators observed enlarged voids and cavities along former gypsum vein traces, with some cavities sufficiently large to admit a human body. The distribution of these features indicated that piping had been concentrated in zones where gypsum veins were most abundant and where hydraulic gradients were steepest, specifically in the upper portion of the abutment immediately beneath the upstream face of the dam. The muddy seepage observed on the morning of March 12 was almost certainly emanating from this zone of active piping, with the transported sediment consisting of clay matrix material liberated as gypsum cement was dissolved away. The mechanical effect of piping within the conglomerate was a progressive reduction in the effective volume of foundation material supporting the dam. As cavities enlarged, the load previously carried by the material removed was transferred to adjacent intact material, increasing stress concentrations and accelerating deformation. In the limiting case, a sufficiently large cavity or interconnected system of cavities could undermine the foundation entirely, leaving portions of the dam base unsupported. Physical evidence suggests that this condition was approached, if not reached, in localized areas beneath the western wing of the dam prior to final collapse. Fragments of the western wing recovered after the failure exhibited zones of concrete that had been in contact with open voids, indicated by clean, unscarred surfaces with no adhering foundation material. On the eastern side of the dam, a different set of physical processes was producing foundation instability. The Pelona schist forming the eastern abutment responded to reservoir filling primarily through changes in pore pressure along foliation planes rather than through bulk material degradation, as in the conglomerate. The foliation in the schist consisted of parallel surfaces defined by aligned mica crystals, separated by distances ranging from a few millimeters to several centimeters. These surfaces were inherently weak and shear due to the low friction coefficient of mica minerals, and due to the absence of significant cohesion or interlocking across the smooth foliation planes. Under dry conditions and with no external loading, the hillside schist was stable because gravitational stresses acting parallel to foliation were less than the available frictional resistance. The impoundment of the reservoir altered this stability balance through two mechanisms. First, the weight of the dam applied a vertical load to the base of the slope, increasing the shear stress acting on potential slip surfaces extending into the hillside. Second, infiltration of reservoir water into foliation planes elevated pore pressures, reducing effective normal stress and thereby reducing frictional resistance. The combined effect was a decrease in the factor of safety, the ratio of resisting forces to driving forces, from a value greater than unity under natural conditions to a value approaching or less than unity under reservoir loading. When the factor of safety falls below unity, the slope is in a state of incipient or active failure, and any additional perturbation, such as increased loading, increased pore pressure, or minor seismic shaking can trigger accelerated movement. The existence of relict landslide surfaces within the eastern abutment meant that pre-existing planes of weakness were present at depth, planes along which most or all cohesion had been lost during prehistoric sliding events. Reactivation of these surfaces required only that pore pressures increase sufficiently to reduce frictional resistance below the threshold value. Geological investigation after the failure identified at least 3 distinct relict slip surfaces within the abutment, oriented subparallel to foliation, and dipping into the hillside at angles between 35 and 45 degrees. The lowermost of these surfaces extended from an elevation near the reservoir shoreline down to a depth estimated at 20 to 30 meters below the dam base. The volume of rock bounded by this surface and by the slope surface was approximately 500,000 cubic meters, a mass sufficient, if mobilized, to displace the entire eastern wing of the dam. The progressive movement of this landslide mass was documented indirectly through the road subsidence observed by the Silve family at 8:30 p.m. on March 12. The road was constructed on the slope surface approximately 30 meters upstream of the dam crest, within the zone of the landslide mass. The observed subsidence of 30 centimeters represented a component of the total displacement vector. The actual 3-dimensional displacement likely included both downward and outward components. Photogrammetric analysis of pre-failure and post-failure aerial photographs, conducted decades after the event, suggested that the total displacement of the slope surface in this area was on the order of 1 to 2 meters by the time of final catastrophic collapse. This displacement occurred over a period of perhaps 6 to 12 hours on March 12, indicating an average movement rate of 2 to 5 centimeters per hour, slow by catastrophic failure standards but rapid compared to typical landslide creep rates. The mechanical coupling between the eastern abutment landslide and the dam structure was direct and unavoidable. The eastern wing of the dam was keyed into the hillside schist, with the upstream and downstream faces of the concrete in contact with excavated rock surfaces. As the landslide mass moved outward and downward, it exerted a distributed force on the dam, tending to push the eastern wing downstream. Simultaneously, the movement removed support from beneath the dam toe, creating a gap between the concrete base and the underlying rock. This combination of increased downstream thrust and decreased foundation support subjected the eastern wing to a loading condition far exceeding its design capacity. The dam had been proportioned to resist hydrostatic pressure from the reservoir through its own weight and through shear resistance on a stable foundation. It had not been designed to resist the active thrust of a moving landslide while simultaneously losing toe support. The relationship between uplift pressure and sliding stability is central to understanding the failure mechanics of both abutments. Uplift pressure, hydrostatic pressure acting on the base of the dam from water that has infiltrated into the foundation, exerts an upward force that reduces the effective weight of the structure. The effective weight is the actual weight minus the uplift force. Frictional resistance to sliding is directly proportional to effective weight. As uplift pressure increases, effective weight decreases, and sliding resistance decreases. For a dam founded on rock with no drainage provisions, uplift pressure at the upstream edge of the base can approach the full hydrostatic head of the reservoir. At the St. Francis Dam, with a maximum reservoir depth of 93 meters, the theoretical maximum uplift pressure at the heel of the dam would be approximately 0.9 megapascals. If this pressure acted over the full base area, the resulting uplift force would have been approximately 40% of the dam's total weight. The actual uplift pressure distribution beneath the St. Francis Dam was not uniform and cannot be reconstructed precisely because no measurements were made prior to failure. However, the limited drainage provisions relief wells beneath the central section only imply that uplift pressures beneath the eastern and western wings were substantially higher than beneath the center. Engineering judgment in comparison with instrumented dams of similar configuration suggest that uplift pressures beneath the undrained sections may have reached 70 to 90% of the theoretical maximum. This magnitude of uplift would have reduced the factor of safety against sliding from a nominal value of perhaps 1.5 to 2 under zero uplift conditions to values potentially less than 1.2% under actual uplift conditions. Combined with the degradation of foundation shear strength in the conglomerate and the active thrust from the landslide in the schist, the sliding resistance margins were minimal or negative in both abutments by the evening of March 12. The catastrophic phase of failure was initiated by the eastern abutment landslide, reaching a critical state of acceleration. Landslides on foliation plains and schist typically exhibit a characteristic failure progression, initial slow creep, followed by accelerating movement as resisting forces are progressively overcome, culminating in rapid runout once a threshold velocity is exceeded and dynamic effects begin to dominate. The transition from slow creep to rapid acceleration can occur over minutes to hours and may be triggered by a specific event such as failure of an intact rock bridge along the slip surface, or sudden increase in pore pressure due to opening of a previously closed fracture. For the eastern abutment at St. Francis, this transition occurred at approximately 11:57 p.m. on March 12, as evidenced by the failure of the electrical transmission line at that moment. The rapid movement of the landslide mass subjected the eastern wing of the dam to forces that exceeded its structural capacity within seconds. The concrete blocks forming the eastern wing, already weakened by shrinkage cracks and potentially by tensile fractures induced by earlier slow movements, were thrust downstream and outward. Eyewitness testimony from Ace Hopewell, who was passing near the dam site at the time of failure, described hearing a deep rumbling sound beginning at approximately 11:57 p.m. This sound was consistent with the fracturing of large concrete blocks and the grinding of concrete fragments against rock surfaces as the eastern wing disintegrated. The breakup of the eastern wing created multiple large fragments, the largest of which, weighing several thousand tons, were carried downstream by the initial surge of water from the breached reservoir. The failure of the eastern wing created an opening approximately 60 meters wide through which reservoir water began to discharge at extremely high velocity. The initial flow through this breach was supercritical flow at velocities exceeding the wave propagation speed in the fluid, and was characterized by intense turbulence and high erosive capacity. This flow scoured the landslide debris that had accumulated at the base of the breach and rapidly eroded the exposed schist foundation. The erosive power of high-velocity water-laden flow is profound. Experimental studies and field observations from other dam failures have documented erosion rates in weak rock exceeding 1 meter per minute under peak flow conditions. At St. Francis, the scour in the eastern abutment removed an estimated 20,000 cubic meters of landslide debris and foundation rock within the first 10 to 15 minutes of breach formation. The central section of the dam, the tombstone, was subjected to altered loading conditions as the eastern wing failed, and the reservoir began to drain through the eastern breach. The loss of lateral support from the eastern side introduced an asymmetric force distribution on the tombstone, with higher stresses on the western edge, where it remained in contact with the not yet failed western wing. The tombstone also experienced hydrodynamic loading from the high-velocity flow passing around its eastern edge. Survey measurements after the failure documented that the tombstone had moved approximately 15 centimeters radially downstream, and a similar distance eastward in the tangential direction. These movements, while small compared to the wholesale displacement of the failed wings, indicate that the tombstone experienced significant stress and deformation during the failure sequence. The fact that the tombstone remained standing while the wings collapsed requires mechanical explanation. The tombstone section was founded on schist, but at a lower elevation than the eastern wing, and the foliation orientation beneath the tombstone dipped more steeply into the foundation rather than parallel to the slope surface. This geometry provided greater resistance to sliding than the orientation beneath the eastern wing. Additionally, the tombstone was the only section of the dam provided with foundation drainage in the form of relief wells. These wells, while modest in number and capacity, apparently provided sufficient pressure relief to limit uplift pressures beneath this section to levels that maintained an adequate factor of safety against sliding. The structural integrity of the tombstone concrete, potentially less compromised by shrinkage cracks than the wings, also contributed to its survival. The combination of favorable foundation geometry, limited drainage, and structural integrity was sufficient to prevent collapse of this section despite the extreme loading conditions imposed during the progressive failure of the adjacent wings. The western wing of the dam failed approximately 20 minutes after the eastern wing, based on analysis of floodwave propagation timing and reservoir drawdown rates. This time interval corresponds to the period required for reservoir level to drop sufficiently that hydrodynamic forces on the western wing changed from the static hydrostatic pressure distribution to a dynamic distribution dominated by drawdown-induced pressures. As water discharged through the eastern breach, the reservoir level adjacent to the western wing dropped rapidly, creating a vertical pressure gradient on the upstream face. This gradient induced additional downstream thrust on the structure. Simultaneously, the partial drainage of the reservoir reduced the confining pressure on the saturated conglomerate foundation, allowing it to expand and further lose strength. The final collapse of the western wing was likely initiated by a combination of continued foundation yielding, increased downstream thrust from drawdown effects, and loss of confining stress from the now displaced central tombstone section. The western wing broke into multiple large blocks along pre-existing shrinkage cracks and possibly along new fractures induced by the altered stress distribution. These blocks were displaced downstream and carried away by the flood flow. The collapse of the western wing created a second major breach approximately 80 meters wide, allowing the remaining reservoir water to discharge through both the eastern and western openings simultaneously. The combined outflow through these two breaches reached peak rates estimated at 14,000 to 16,000 cubic meters per second flow rates that drained the reservoir to near-empty conditions in approximately 70 minutes from the initial failure. The erosion of foundation material during the flood discharge was extensive. In the western abutment, approximately 6 meters of conglomerate was removed over an area of several thousand square meters, exposing the underlying schist and fault zone. In the eastern abutment, landslide debris and weathered schist were scoured to depths of 10 to 15 meters, creating a channel substantially below the original valley floor elevation. The erosive action was concentrated in the first 30 to 40 minutes of discharge, when flow velocities were highest and when the flow was heavily laden with sediment that enhanced its abrasive capacity. As the reservoir level dropped and flow rates decreased, erosion rates diminished correspondingly. By the time the reservoir was nearly empty, erosion had essentially ceased, leaving a stable channel geometry that was documented in post-failure surveys. The mechanical work performed by the flood, the energy expended in breaking apart the dam, eroding foundation material and transporting debris downstream can be estimated from the change in potential energy of the reservoir water. The reservoir contained approximately 47 million cubic meters of water at an average elevation approximately 45 meters above the downstream valley floor. The total potential energy was therefore approximately 20 billion joules. A substantial fraction of this energy was dissipated through turbulence and frictional heating as the water flowed through the breaches and down the canyon. However, sufficient energy remained to perform the observed work, fragmenting concrete into blocks weighing thousands of tons, eroding tens of thousands of cubic meters of rock and soil, and transporting debris over distances exceeding 1 kilometer. The largest transported block fragment of the dam's central section, weighing approximately 10,000 tons, was carried more than 1,200 meters downstream from the dam site and was deposited on a hillside approximately 20 meters above the valley floor. The mechanics of transporting such a massive block in a flood flow involve complex interactions among buoyancy, drag, lift, and impact forces. The block must have been rendered nearly neutrally buoyant by the high sediment concentration in the flow, reducing its effective weight to a small fraction of its in-air weight. Once buoyant, the block would be carried in the flow much like a large raft, tumbling and sliding over the irregular bed topography until it came to rest in a location where flow velocity decreased, or where it became lodged against an obstruction. The point of no return in this failure sequence, The moment beyond which catastrophic collapse was inevitable regardless of any intervention, is difficult to define precisely but can be constrained by analysis of the failure mechanisms and their progression rates. If the reservoir had been rapidly drawn down on the morning of March 12, following Mulholland's inspection, the removal of hydrostatic pressure would have reduced driving forces on both the conglomerate foundation and the eastern abutment landslide. However, the subsurface damage that had already occurred piping cavities in the conglomerate, elevated pore pressures in the schist, would not have been immediately reversed by drawdown. Pore pressures in low permeability rock require days to weeks to dissipate following a change in boundary conditions. Cavities created by piping erosion do not refill with intact material when water is removed. It is therefore plausible that even a rapid drawdown initiated on March 12 morning would not have prevented failure, although it might have delayed or mitigated the consequences. The point of no return was likely reached several days earlier, when piping erosion in the conglomerate had progressed to the stage where foundation support had been critically compromised and when pore pressures in the schist had risen to levels where the eastern abutment landslide was in a state of incipient instability. Once these conditions were established, the failure became a question of timing rather than of whether failure would occur. The specific triggering event, whether it was continued piping erosion reaching a critical cavity size, or the eastern landslide reaching a threshold pore pressure, or some combination, determined the exact moment of collapse but did not determine whether collapse would occur. This analysis establishes that the failure of the St. Francis Dam was the result of multiple interacting mechanisms, each of which was individually capable of compromising stability and which collectively created a failure chain in which no single link could be identified as the sole cause. The conglomerate foundation was inadequate, the schist abutment was unstable, the fault provided a seepage path, the absence of drainage allowed uplift pressures to develop. The monolithic structure could not accommodate differential movements. The increased height reduced safety margins. No single one of these conditions caused the failure, all of them together made failure inevitable. The collapse of the St. Francis Dam occurred with such rapidity that no stabilization attempts were possible during the terminal failure sequence. From the initiation of catastrophic eastern abutment failure at 11:57 p.m. to the complete drainage of the reservoir. Approximately 70 minutes later, events unfolded at a pace that precluded any human intervention. However, the period following the failure, extending from the immediate aftermath through the subsequent weeks and months, involved intensive efforts to assess the extent of damage, to search for and recover victims, to prevent secondary failures that might cause additional casualties, and to determine the causes of the disaster. These post-failure activities, while not stabilization attempts in the conventional sense of arresting an ongoing failure, nevertheless constitute an essential component of the forensic reconstruction, because they reveal what could not be known during the hours preceding collapse, and because they establish the factual foundation for subsequent analysis. The first awareness that a catastrophic failure had occurred came from residents and travelers in San Francisco Canyon, who heard the initial collapse or who encountered the rapidly advancing flood wave. Ace Hopewell, whose motorcycle journey brought him past the dam site at approximately midnight, heard a deep rumbling noise that he initially attributed to blasting operations at a nearby construction site. Within minutes, he encountered floodwaters on the canyon road and narrowly escaped to higher ground. His subsequent report to authorities provided one of the earliest confirmations that a major disaster was underway. Similarly, the power company substation downstream of the dam recorded the failure of electrical transmission lines at 11:57:30 p.m., providing an objective timestamp for the initial structural failure. However, the significance of this electrical fault was not immediately recognized by power company personnel, who initially interpreted it as a routine equipment failure rather than as an indicator of dam collapse. The first confirmed communication of the dam failure to municipal authorities occurred at approximately 12:30 a.m. on March 13, when a telephone call reached the Los Angeles Bureau of Waterworks and Aqueduct offices reporting that the dam had collapsed and that flood waters were moving down the Santa Clara Valley. This report prompted immediate efforts to warn downstream communities. telephone operators in Los Angeles began placing calls to police departments, fire departments, and other emergency services in towns along the anticipated flood path. The effectiveness of these warnings varied considerably depending on the time available before flood arrival, the adequacy of local communication infrastructure, and the ability of local authorities to alert residents and facilitate evacuation. In the town of Castaic, located approximately 8 kilometers downstream of the dam, virtually no warning was possible because the flood wave arrived within 45 minutes of the initial failure. Most residents were asleep, and the arrival of the flood at approximately 12:45 a.m. provided no opportunity for organized evacuation. The town sustained near-complete destruction of structures in the flood path, with casualties concentrated among residents of low-lying areas adjacent to the creek channel. In contrast, the towns of Fillmore and Santa Paula, located 35 and 42 kilometers downstream respectively, received telephone warnings approximately 1 to 2 hours before flood arrival. Local authorities used fire sirens, telephone chains, and direct door-to-door notification to alert residents. While the warnings were not universal, some residents did not hear the alerts or did not have time to reach high ground. The advance notification significantly reduced casualties compared to what would have occurred without warning. William Mulholland was notified of the dam failure at approximately 1 a.m. on March 13th. He immediately traveled to the dam site. Arriving at approximately 3:30 a.m. by this time, the reservoir had drained completely, and the extent of the structural collapse was visible in the darkness by the light of vehicles and portable lamps. Mulholland's initial assessment, based on visual observation of the remaining tombstone section and the massive breaches on either side, was that the dam had failed catastrophically and that the failure involved both abutments. He made no immediate public statement regarding the cause of the failure, but his private communications to Bureau staff indicated shock and profound personal distress at the magnitude of the disaster. The immediate priorities in the hours and days following the failure were search and rescue, recovery of bodies, provision of emergency shelter and medical care for survivors, and assessment of infrastructure damage. Search and rescue operations began at first light on March 13th and continued for several weeks as teams systematically searched the flood-affected area for victims and survivors. The physical conditions were extraordinarily difficult. Debris fields containing building fragments, uprooted trees, agricultural equipment, and large blocks of concrete from the dam covered extensive areas. Mud and sediment deposits in some locations exceeded 2 meters in depth, and many bodies had been carried far downstream or out to sea. Recovery teams used dogs, helicopters, and systematic ground searches to locate victims. The process of identifying recovered bodies was complicated by the violence of the flood, which in many cases caused severe trauma that made visual identification impossible. Dental records, personal effects, and witness testimony were used to establish identities where possible. The engineering response to the disaster involved multiple parallel investigations conducted by different organizations and jurisdictions. The Los Angeles County coroner convened a formal inquest to determine the cause of death for identified victims and to assess legal responsibility for the disaster. The coroner's jury heard testimony from witnesses, reviewed physical evidence, and received expert opinions from engineers and geologists. The California governor appointed a commission consisting of civil engineers and geologists to investigate the technical causes of the failure and to make recommendations for preventing similar disasters. The Los Angeles Bureau of Water Works and Aqueduct conducted its own internal investigation. Professional engineering societies, including the American Society of Civil Engineers, assembled independent review panels to examine the failure and to disseminate lessons learned to the broader engineering community. These multiple concurrent investigations produced overlapping but not always consistent findings, reflecting differences in methodology, access to evidence, and interpretive frameworks. The physical evidence available for forensic analysis consisted of the damaged and partially destroyed dam structure, the scoured foundation surfaces exposed after the flood, displaced blocks of concrete distributed along the canyon, and material samples that could be collected for laboratory testing. Access to the site was complicated initially by residual flooding, unstable debris piles, and ongoing search and rescue operations. Systematic engineering surveys of the site did not begin until several days after the failure, by which time some evidence had been disturbed by rescue activities and by natural weathering. Nevertheless, the investigation teams were able to document key features, including the final position and orientation of the tombstone section, the locations and dimensions of the eastern and western breaches, the extent of foundation scour, the positions of major displaced concrete blocks, and the characteristics of exposed foundation rock. One of the critical forensic questions was the sequence of failure, specifically whether the eastern or western wing had failed first. This question was significant because the answer would indicate which foundation condition was most critical and which failure mechanism was dominant. Early speculation favored western abutment failure, based on the observation that the conglomerate was obviously weak and that precursor seepage had been concentrated in the western abutment. However, more detailed analysis of the evidence pointed toward eastern abutment failure as the initiating event. The electrical transmission line failure timestamp at 11:57:30 p.m. corresponded to disruption of lines supported on the eastern abutment, indicating that large-scale movement in this area occurred at the moment of initial failure. The road subsidence observed by the Silve family 3 hours earlier provided direct evidence of active landslide movement in the eastern abutment prior to collapse. The pattern of erosion and debris distribution suggested that the initial breach occurred on the eastern side, with westward propagation of the failure following the lowering of reservoir level. The discovery of extensive landslide features in the eastern abutment was made during detailed geological mapping conducted in the weeks following the failure. Geologist Bailey Willis, who participated in one of the investigation commissions, identified multiple relict slip surfaces within the schist and recognized that the hillside had been the site of prehistoric slope failures. This finding was significant because it indicated that the instability of the eastern abutment was not a consequence of dam construction, but rather a pre-existing geological condition that had been reactivated by reservoir loading. Willis's interpretation was that the combination of increased loading from the dam's weight and elevated pore pressures from reservoir infiltration had reduced the factor of safety of these ancient landslides below the threshold for stability, initiating renewed movement that culminated in catastrophic failure. The weakness of the Vasquez conglomerate was confirmed through laboratory testing of samples collected from the western abutment area. Specimens were subjected to unconfined compression testing, triaxial testing under confined conditions, and immersion testing to characterize swelling behavior. The results documented compressive strengths in the saturated state of less than 1.5 megapascals, and significant volumetric expansion upon wetting. Additional testing examined the solubility of gypsum veins and the rate at which dissolution could create enlarged seepage paths. These laboratory results provided quantitative confirmation of what had been inferred from field observations. The conglomerate was fundamentally unsuitable as a foundation material for a high dam and would inevitably undergo progressive deterioration when subjected to sustained saturation. The examination of the tombstone section provided important evidence regarding the behavior of the dam structure during failure. Survey measurements documented that the top of the tombstone had moved approximately 15 centimeters downstream and a similar distance in an eastward tangential direction relative to its original position. This movement indicated that the tombstone had experienced significant loading during the failure sequence, but had not undergone complete collapse. The discovery of a crushed wooden ladder at the base of the western side of the tombstone, documented by engineer Carl Grunsky, suggested that the tombstone had tilted or rotated slightly before settling back into a near-vertical position. The presence of sheared concrete surfaces on the lower steps of the tombstone indicated that tensile failure had occurred in the outer layers of the structure, separating a thin shell from the main mass. One of the secondary crises that emerged during the post-failure investigation was the discovery that other dams designed and constructed under Mulholland's direction might be vulnerable to similar failures. The Hollywood Dam, from which the St. Francis Dam design had been directly copied, was immediately subjected to intensive inspection and analysis. This inspection revealed that the Hollywood Dam also lacked adequate foundation drainage and had developed shrinkage cracks similar to those observed at St. Francis. However, the Hollywood Dam was founded on granite rather than on weak sedimentary or metamorphic rock, and the foundation conditions were judged to be significantly more favorable. Nevertheless, the dam was retrofitted with additional drainage provisions and was subjected to ongoing monitoring to ensure its continued safety. Other Los Angeles aqueduct structures were similarly inspected, and in some cases modified to address potential vulnerabilities. The question of whether any intervention on March 12, following Mulholland's morning inspection, could have prevented the catastrophic failure was extensively debated during the coroner's inquest and the various commission investigations. The most obvious potential intervention would have been rapid drawdown of the reservoir by opening outlet valves and allowing water to discharge through the dam's outlet works. The outlet works at St. Francis consisted of a valve-controlled conduit with a maximum discharge capacity of approximately 10 cubic meters per second, far less than the average inflow rate from the aqueduct, but sufficient to lower reservoir level gradually if inflow were simultaneously halted. Complete drainage of the reservoir through the outlet works would have required approximately 50 days of continuous discharge at maximum capacity with zero inflow. A more rapid drawdown could have been achieved by using the spillway, which had a much larger discharge capacity but which could only be activated once reservoir level rose to spillway crest elevation. On March 12, the reservoir was at spillway level, meaning that water was already discharging over the spillway at a rate matching the net inflow from the aqueduct minus any outlet works release. Increasing spillway discharge would have required reducing inflow by closing aqueduct valves upstream, which would have allowed reservoir level to drop below spillway crest. Once below spillway crest, further drawdown would have required outlet works discharge only, reverting to the slow drawdown rate. Even under the most aggressive drawdown scenario, immediate closure of aqueduct inflow and maximum outlet works, discharge reservoir level could not have been lowered more than a few meters in the 12 hours between Mulholland's morning inspection and the time of actual failure. The mechanical effectiveness of this partial drawdown in preventing or delaying failure is uncertain. Lowering reservoir level by several meters would have reduced hydrostatic pressure on the dam and would have reduced the hydraulic gradient driving seepage through the foundation. However, it would not have immediately reduced pore pressures within the foundation rock, which respond to boundary condition changes over timescales of days to weeks depending on rock permeability. The cavities created by piping erosion in the conglomerate would not have been repaired by drawdown. The eastern abutment landslide, already in a state of progressive movement, would likely have continued to deform even with reduced reservoir loading. The most probable outcome of an aggressive drawdown initiated on March 12 morning would have been a delay of failure, by hours to perhaps days, rather than a prevention of failure. The broader question of whether the failure could have been prevented through different decisions made during design and construction admits of a more definitive answer. If a comprehensive geological investigation had been conducted prior to site selection, the presence of weak conglomerate, foliated schist, relict landslide surfaces, and the San Francisco Fault would have been documented, and the site would likely have been rejected as unsuitable for a high dam. If rigorous structural analysis had been performed, the inadequacy of the dam's proportions after the height increase would have been identified, and either the base width would have been increased or the height increase would have been rejected. If foundation drainage had been provided beneath the full length of the dam, uplift pressures would have been controlled, and factors of safety against sliding would have been higher. If independent technical review by a state agency or external consultants had been required, any of these deficiencies might have been identified and corrected. The absence of these safeguards meant that prevention of failure would have required recognition of the problem and initiation of corrective action during the operational phase specifically. During the period of reservoir filling when the effects of foundation saturation and increased loading were becoming manifest, the observed increases in seepage, the development of turbidity, and the surging flow pattern on March 12 were symptomatic of progressive failure, but these symptoms were ambiguous and could be rationalized within a conceptual framework that did not include subsurface erosion in rock foundations or landslide reactivation as credible mechanisms. A more conservative interpretation of these warning signs would have prompted reservoir drawdown as a precautionary measure, but such conservatism was not part of the operational culture or the decision-making framework in place at the time. The institutional response to the disaster included immediate changes to California's dam safety regulatory framework. Within weeks of the failure, the state legislature began consideration of amendments to eliminate the exemption that had allowed municipal agencies to construct dams without state review. The legislation that ultimately passed in 1929 gave the California Division of Water Resources authority to review and approve all dam designs regardless of ownership, to inspect dams during construction, and to require modifications to existing dams found to be unsafe. This legislation established one of the first comprehensive state-level dam safety programs in the United States and served as a model for similar programs adopted in other states in subsequent years. Professional engineering practice was also affected by the disaster. The failure prompted increased emphasis on geological site investigation as a mandatory component of dam design. Engineering curricula began to include more extensive treatment of foundation mechanics, soil and rock behavior, and the importance of subsurface exploration. Professional societies developed and disseminated guidelines for dam design that emphasized the need for formal calculations of stability, consideration of uplift pressure, provision of drainage, and inclusion of appropriate factors of safety. The concept of independent technical review, whereby significant projects are subjected to examination by engineers not affiliated with the design team, gained wider acceptance as a means of identifying potential errors or oversights before construction. The human dimension of the post-failure period was profound and extended far beyond the immediate casualties and property losses. Survivors who had lost family members, homes, or livelihoods faced lengthy processes of recovery and rebuilding. The psychological trauma of the disaster affected not only direct survivors but also rescue workers, investigators, and community members who witnessed the destruction. William Mulholland, who had built his professional reputation on the successful delivery of water infrastructure to Los Angeles, was personally devastated by the failure. He testified at the coroner's inquest, accepting full responsibility for the disaster and stating that no blame should attach to any other person. He resigned from his position at the Bureau shortly afterward and lived in relative seclusion until his death in 1935. His legacy remains complex. He is remembered both as the visionary engineer who made possible the growth of Los Angeles through the construction of the aqueduct system, and as the engineer whose errors led to one of the deadliest civil engineering disasters in American history. The forensic investigations collectively identified multiple contributing factors, but did not reach unanimous agreement on the relative importance of different factors or on the precise sequence of events. The California Governor's Commission concluded that the failure was due primarily to defects in the foundation, specifically citing the weakness of the conglomerate and the presence of ancient landslides in the schist. The coroner's jury reached a similar conclusion, but added that there had been an error in engineering judgment in the design and construction of the dam. Professional engineering panels emphasized the absence of adequate foundation investigation, the inadequacy of drainage provisions, and the failure to perform rigorous stability calculations. All investigations agreed that the disaster was preventable, and that it resulted from a combination of geological unsuitability of the site and engineering deficiencies in design and construction. One of the persistent uncertainties that remained after the investigations was the question of whether the dam could have survived if only one of the two abutment problems, the conglomerate weakness or the schist instability, had been present without the other. This counterfactual analysis is inherently speculative, but is relevant to understanding which failure mechanism was most critical. If the eastern abutment had been stable, would the progressive yielding of the conglomerate foundation alone have caused collapse, or would the dam have simply settled and deformed without total failure? If the conglomerate had been competent, would the eastern abutment landslide alone have caused collapse? The evidence suggests that either condition alone might have been manageable, particularly if adequate drainage had been provided to control uplift pressures. However, the combination of both conditions, along with the absence of drainage, the inadequate structural proportions, and the monolithic construction without joints, created a configuration in which failure was highly probable and ultimately inevitable. The secondary crisis of assessing the safety of other existing dams and water structures in California and nationwide was addressed through systematic inspection programs initiated by state and federal agencies in the years following the St. Francis failure. These inspections identified numerous dams with deficiencies similar to those at St. Francis: inadequate foundation investigation, insufficient drainage, lack of formal stability calculations, and absence of independent review. Many of these dams were retrofitted with drainage systems, spillway improvements, and structural reinforcements. Some were partially or completely removed if remediation was judged to be impractical or if the risk was deemed unacceptable. The net effect was a substantial improvement in the overall safety of the dam inventory, driven by the recognition that past practice had been inadequate and that higher standards were necessary to prevent future disasters. The economic costs of the disaster extended beyond the direct property damage and loss of life. The city of Los Angeles faced claims for damages totaling many millions of dollars, filed by survivors and by the estates of deceased victims. The legal proceedings extended over several years and ultimately resulted in settlements totaling approximately $15 million in 1928 currency, equivalent to several $100 million in present value. The financial burden was borne by Los Angeles taxpayers through bond issues and rate increases. The reputational damage to the city and to the Los Angeles Bureau of Waterworks and Aqueduct was significant and long-lasting, affecting public confidence in municipal water infrastructure and in the competence of public agencies to manage large-scale engineering projects. The St. Francis Dam site itself was not redeveloped as a dam location. The surviving fragments of the dam, the tombstone section and portions of the western wing wall, were demolished in 1929 to remove hazards and to prevent their presence from serving as a memorial to the disaster. The reservoir basin reverted to natural drainage, and the area remained largely undeveloped for decades. In subsequent years, the site has been recognized as historically significant, and efforts have been made to preserve the remaining evidence of the dam and to interpret the disaster for educational purposes. The location is now accessible to visitors and serves as a sobering reminder of the consequences of engineering failure. The question of what could be known in the immediate aftermath of the failure versus what could only be determined through extended forensic investigation is central to understanding the stabilization and recovery period. In the first hours after collapse, observers could see that the dam had failed catastrophically, that both abutments had been involved, and that the reservoir had drained completely. They could not determine the sequence of failure, the specific mechanisms that had initiated collapse, or the relative contributions of different factors. These determinations required systematic investigation, geological mapping of the abutments, laboratory testing of foundation materials, structural analysis of the dam proportions, and reconstruction of the sequence based on physical evidence and witness testimony. The investigations took months to complete, and their conclusions were debated for years afterward, reflecting the inherent difficulty of reconstructing complex failure sequences from post-event evidence.